All right, here's the warm-up problem. And I just wrote it out here. This is the integral that we have to solve, but the book tells us that the way that we're going to solve it is by appropriately switching the order of integration. All right, so to begin with, let's sketch the region of integration. All right, so let's look. So to do that, let's look here. So this is the first integral we're doing. We're doing it with respect to y. So let me sketch out, here's z, here's x, and here's y. And what all of our integrals are doing is they're starting on the curve y is equal to x squared. So it's going to look like this. Here's what that looks like. And of course, this is going to extend upwards along z. So it's really kind of like this. So. And what we're doing is we're integrating with respect to y from that up until y is equal to 1. So like this, all the way up. Right, so imagine I'm integrating this way. So that'll take care of these two integrals, right? Because I'm integrating from 0 to x squared. I stop when y is equal to 1. And you can see that when y is equal to 1, I come out here. That's going to come out to x is equal to 1, like this. And then how big a region am I integrating? Well, I go from z is equal to 0 to 1. So let's say that this here is z is equal to 1. Then this here is my region of integration. Okay. All right. So let's look at these two pieces. And suppose that I wanted to switch the order of integration. And instead of integrating dy dx, I wanted to go dx dy. What would that look like? Well, it would look like integrating this way first, right? Integrating horizontally. So let's look sort of down on it. Here's x, here's y. Here's 1 and 1. So we started integrating this way, starting on this curve y is equal to x squared and ending at 1. Now what we're going to do is think about going this way and see if that's going to help us at all. So this is going to be, we're going to end, it's the function y is equal to x squared, but we're coming out here at a fixed y, so x is going to end at the square root of y. So this is going to be x is equal to root y is where we end. So our inner integral now would look like the integral from 0 to the square root of y. Our function stays the same, 12x z e to the zy squared. We're going to have now a dx. And then when I integrate with respect to y, I go from 0 to 1. And let's look at this and see if it gets us anything. Well, when I integrate it, I'm going to, with respect to x, I get an x squared over 2 here. But the important part is the x squared. Because when I now evaluate it at the square root of y, I'm going to get a y e to the y squared. That allows me to do a substitution and solve this integral, whereas previously here, I couldn't integrate the e to the y squared. So this, by changing the order of integration, I'm going to be able to solve this integral. And of course, we're integrating from 0 to 1 with respect to z. All right, so this is the integral that we need to solve. that's the appropriate change of the order of integration that's going to allow us to solve it. So let me bring this up, and then we'll go ahead and get the solution. All right. Let's start evaluating. This is the only x in my expression, so when I integrate with respect to x, I get an x squared over 2. Evaluated at root y gives me integral from 0 to 1, integral from 0 to 1. I get that x squared over 2, so let's make it 6 times the square root of y squared, so that gives me y, z, e to the zy squared, dy, dz. Now let's do this substitution. U is equal to zy squared. Du is equal to 2zy dy. I can write this as 3 times 2. And now I have this 2zy dy, and so I'll just plug things in. All right, so when y is equal to 0, u is equal to 0, and when y is equal to 1, u is equal to z. Then I get 3, 2zy dy is going to be du. This becomes e to the u, dz. All right, now I'm going to integrate e to the u with respect to u, so I get integral from 0 to 1 of 3 e to the u evaluated from 0 to z, dz. That becomes the integral from 0 to 1, 3. This is going to be e to the z minus e to the 0, which is 1, dz. Then I can do this integral, so the integral of 3e to the z is just going to be 3e to the z, and the integral of -3 is going to be -3z. And I'm evaluating this from 0 to 1. So I get 3e to the 1 minus 3e to the 0, which is just going to be -3, minus 3 times 1, minus 3 times 0, which is 0. So I get 3 times e to the 1 minus 2. And that's what I get for my final answer.